Hi folks, I'm going to show you today how to compile an open source discrete element method or DEM solver called LIGGGHTS. It was released in 2011 and it's based on the molecular dynamics solver LAMMPS, which is quite known in the scientific community. It's been used for simulating all kinds of different systems, nanosystems, polymers, anything of interest to material scientists, to biologists like biomacromolecules, proteins, nucleic acids, and so forth. It's just a very efficient m-body solver. That's really what LAMMPS is. And LIGGGHTS is an improved version of that for granular systems. So in addition to that, LIGGGHTS provides coupling to CFD, or computation fluid dynamics, which is of great interest to engineers, especially working in the industry, because this way you get to simulate more realistic systems and include things like air effect. Now, today I'm going to show you how to compile LIGGGHTS on Linux. I'm using here Fedora 22, and I'm going to show you how to compile this basically from the source code. If you're using Ubuntu, for example, it should be a very similar process. The first thing to do is to copy this link, which I will post in the video below. This is basically the repository for LIGGGHTS public on GitHub. And if you don't have Git set up on your system, you're going to have to just download the zip file and manually extract the files. Otherwise, just copy the link, and then I'm going to go to my terminal here, and I'm gonna simply clone this repository. Now, depending on the speed of your connection, this might take a few seconds to a few minutes. So I'm gonna fast forward here until this is done, because I'm connected to Wi-Fi and my connection is just too slow.
So now that the download is complete, we should have a new directory called LIGGGHTS public. So we're going to change directory to LIGGGHTS public and list all the files in that directory. Now, if you chose to download the source code with a zip file instead, then you'd have to unzip the files into a new directory. You can call it LIGGGHTS public or whatever you want, and then you're going to have to change directory to source, because that's where all the make files are that we're going to need to compile LIGGGHTS. If you list all the files in source, you see that we have a lot of C++ and header files, and also a few directories for installing extra packages for LIGGGHTS. Of particular interest to us is this make file and the make directory, which contains a set of predefined make config files. So if we list all the files in make, you're going to see that we have different make config files for different computer architectures. Some of these are for Cray machines, others are for Fedora, Ubuntu, VTK, and so forth. So what we're going to do here is go for a standard, I guess you can call it a standard MPI implementation of LIGGGHTS. So I'm going to go ahead and edit the makefile .openmpi. Now, if you don't have your system configured with openmpi, if it's mpi-ch2, it's going to be very similar. I'm using here a GCC compiler. You can use a different compiler, but you might have to tweak the settings in the makefile a little bit. So, using your favorite text editor, you can open makefile.openmpi. And the first thing I'm going to do before editing anything in this file is I'm going to go ahead and save this as a new file. Let's call this Fedora_MPI. You can call this anything you want, anything descriptive that you can remember. And once it's saved, we're going to look at the different settings and how to tweak these. So the compiler CC is MPI-C++. It may not necessarily be MPI-C++ on your system. So one way to verify this is correct is to open a new tab, and let's see which MPI-C++ it exists. It's in user bin MPI-C++. On certain machines, this could be MPI-CC, capital CC. And as you can see here, I also have that configured. In fact, the MPI-CC is the OpenMPI executable, right? This is just a GCC compiler wrapped up with the OpenMPI libraries. If we try and see what's the difference between both of these, oh, it's a symbolic link. So the MPI C++ is exactly the openmpi MPI C++. So we're good. That should work. We go back to the CC flags. Now these are specific to the compiler you're using. For GCC, this should be enough. I'm using a second level optimization because I'm interested in production runs. For debugging reasons, you can change this to 0 level optimization. If you're using a different compiler like Clang, you might have different options to set here. They're definitely not going to be the same. All the rest of these, I'm going to keep them intact simply because I'm not interested today in compiling LIGGHTS as a shared library. So I'm not going to change anything in the shlib flags. So you can keep these intact if you're just interested in compiling a static executable file for LIGGHTS. Now, if you're interested in compiling LIGGHTS with VTK, then you're going to have to add here another option for VTK. I'm not going to do that today. And for the MPI include path and library variables, I'm not going to set these either because LIGGHTS is going to automatically figure these out. It's not going to be a problem. Now the FFT, on the other hand, this is a legacy part of LAMPS. FFT stands for fast Fourier transforms, and these are used usually in molecular dynamics for computing long-range forces efficiently. So in DEM, the forces are usually short-range forces. They're just contact forces, so we don't really need FFT. LIGGHTS does not use FFT in any part of its code. So there's really no reason to keep these variables. We can delete them, or better yet, we can just get rid of the FFT, include path and library variables, and the extra include path and library variables over here, so that we'd be eliminating all the FFT dependencies during compilation and linking. If we don't do that, if we try to compile this, and if you don't have FFTW, which is a specific library that implements fast Fourier transforms efficiently, I don't have that installed on my system, so the compilation will not work. So one way to get around that is just to get rid of the FFT dependency here, which again is something we don't need anyhow. We don't really need the FFT. So this, I think, is the best way to avoid any potential problems or to have to install FFTW. So we're going to save this. I'm going to close this file. I'm going to go back to our terminal. And now we're basically ready to compile LIGGHTS. Now, the first thing to do is to make sure that any previous object files due to any previous compilation are deleted. So we're going to invoke make clean -all. That's going to delete any, let's just call these garbage object files that are completely unneeded. We're going to make a fresh compilation here, so we're going to invoke make Fedora _MPI, which is the name of the make config file that we created. And that should basically do it. Now the compilation can take a few minutes depending on the speed of your machine, but usually it takes, say, 5 to 10 minutes tops. Shouldn't take longer than that, and everything works out, you should end up with a LIGGHTS executable file. So now that the compilation is done, you should have a new executable file called lmp_fedora_mpi. So this extension here, Fedora_mpi, could change depending on the name of the config file you chose to compile LIGGHTS. So we're gonna list the files in this directory, and we should see the executable is right over here. It's the last file created, and that's pretty much it. Now we can use this to basically run DEM simulation. One final step I like to do, and this is totally optional, is to create a symbolic link to the LAMPS Fedora MPI executable so that I can call it from any other location. I don't have to be in this particular directory. And to see where we are right now, we're going to use print working directory, and right now I'm in my downloads LIGGHTS public source directory. Now this could change depending on where you decided to download and compile LIGGHTS. So I'm going to create a symbolic link to the LAMPS Fedora MPI executable, giving it the full path, and the link is, I'm going to place it in my .local bin and let's just call this lights underscore MPI. Now I chose .local bin because this path is included in my path environment variable. It could be just anywhere you want, but usually you want to include this in a location that's included in your path environment variable, so that you can basically call it from any location on your system. So with this, we can see that the symbolic link is created. Now if I go to a new tab and say which lights MPI, it's going to give me it's located in my .local bin lights MPI. To test if this works, what we're going to do is simply invoke lights underscore MPI, enter, and if it works, you should get exactly this. You should get the version of lights. In my case it's 3.6.0. this is the latest version. It should give you the date of the compilation, username, and the commit specific to Git. Control D will exit. Now if you chose not to create a symbolic link, then you can just directly execute the lights executable file and get basically a similar result. So the // will execute the LMP Fedora MPI executable, and if I press enter, I'm going to get basically a similar result. Control D exits. Now the only drawback to this method is you can only execute the LMP Fedora MPI file if you're in the source, in the lights public source directory. So that's why a symbolic link is just more convenient. Now let's run a simple test case just to see if lights is going to work for real simulation. So I'm going to go back and list all the files in the lights repository. As you can see here, we have an examples directory. So I'm going to go in there and then go into lights tutorials public. If you list all the files here, you're going to see that we have many systems that we can try lights on. I'm going to specifically go for here, let's see, moving mesh LAN. And if I list all the files, you can see that we have, this is the input script file, we got the meshes directory, this is for the results, mostly the trajectory files that the simulation would generate, and then we have two scripts for running the simulation. So we're going to go ahead and take a look at the run script with gedit. It's a very simple script, so it's simply invoking the lights executable file, and then the input script file is going to be given as an argument to lights. Now this will not work simply because the lights executable file does not exist. So we called the lights executable file lights underscore MPI, or anything you chose for the lights executable. I'm going to save that, I'm going to exit, and then I'm going to run the run script. As you can see here, lights works. We're doing the simulation, and we can then, once the simulation is done, start doing post analysis.